This is part 2 of the video series on simulating the 4-tank system in MATLAB-Simulink. In this video, we'll focus on developing a controller to regulate the water levels in the tanks. Tanks 3 and 4 can be treated as single input, single output SISO systems, since their levels can be directly controlled by adjusting the output of the pumps. For these tanks, a simple PID-based feedback controller is sufficient. However, tanks 1 and 2 behave as a multi-input, multi-output MIMO system. This is because both pumps influence the levels of both tanks, and the interconnection between the tanks makes it impossible to control their levels independently using a regular PID approach. Therefore, a more advanced control strategy is required. In this video, our main objective is to design a controller capable of accurately regulating the levels in Tank 1 and Tank 2. We'll explore two different methods to control and compare the results in this video. To begin with, let's define constants and initial conditions of the equations. For this video, I am taking the parameters from the papers widely used for this 4-tank systems. The equations that we have modeled in previous video have square root terms which cause to non-linearity. Because of that, designing a controller becomes more difficult. The 4 equations defining the process of the tanks can be solved by Taylor series expansion at the operating point and Jacobian matrix transformation to get a state space form of 4-tank system. But in this video, we are using MATLAB-Simulink to find the operating point and linearize at that point. Before finding the operating point, we need to understand the concept of minimum and non-minimum phase. The flow from pump is divided by a three-way valves represented by the parameters gamma 1 and gamma 2. Gamma 1 and gamma 2 determines whether the system behaves as a minimum phase or non-minimum phase process. If gamma 1 plus gamma 2 is greater than 1 but less than 2, the system is minimum phase and its zeros lie in the left half plane. If gamma 1 plus gamma 2 is less than 1, the system is non-minimum phase and the zeros lie in the right half plane. And if gamma 1 plus gamma 2 is exactly 1, the zero is located at the origin, making it a special edge case. In full-scale control, minimum and non-minimum phase should be linearized separately and find the control parameters individually. But in this video, we are using the minimum phase and keeping gamma 1 and gamma 2 constant all the times. To find the operating point, we're going to find the steady state condition at a certain flow, assuming the maximum flow possible from the pump at 20 cm3 per second. We'll find the steady state values of all tanks at 10 cm3 per second of flow, that is half of the maximum flow possible. Now, we begin the linearization of the system at the operating point. Since we are only concerned in the level of tank 1 and tank 2, for simplicity, we will only find the state space and transfer function models for 2 inputs and 2 outputs only. However, we can also get the linearized models including 2 inputs and 4 outputs that later choose the tanks 1 and 2 as outputs. After following all the steps as done in the video, Model Linearizer app in Simulink gives the Linearization 1 that can be exported to the MATLAB workspace. The Linearization 1 contains the state space model and transfer function models of the 2 inputs and 2 outputs. Altogether, we get a state space model with 4 states, H1, H2, H3, H4, 2 inputs, QA and QB, and 2 outputs, H1 and H2, and 4 transfer function models. Although controlling level of tank 3 and 4 is not of our interest, we are going to demonstrate a simple feedback-based PID control scheme to control their levels, since these can be considered as a single input, single output system, as the pump QA only affects tank 4 and pump QB only affects tank 3. We are going to tune this PID controller by using auto-tune feature of Simulink. You can use any other method to tune this PID. Upon simulation, it has been found that with maximum pump flow of 20 cubic centimeter per second, it is not possible to reach the height of 14 and 16 centimeters, which is taken as a reference level for simulation. To match the reference level, we need pump of at least 35 cubic centimeter per second of capacity. The point here is, if tank 3 and 4 are only to be controlled, a regular PID controller is sufficient. The model predictive control MPC is an advanced method of process control that has been in use in various processes, especially in multi-input, multi-output systems. Here, I am going to demonstrate how a MPC controller can be designed for a MIMO system. Model predictive control works on the principle of minimizing the cost function equation as shown. The tuning of MPC involves adjusting these parameters to balance performance and control effort. Prediction horizon P. A longer prediction horizon allows the controller to anticipate future behavior more accurately, improving long-term performance, but increases computation time. A shorter horizon reduces the computational load, but may result in short-sighted decisions. Control horizon M. This defines how many future control moves are optimized. A short control horizon results in smoother and more conservative actions, while a longer horizon increases flexibility and responsiveness, but may introduce instability or excessive actuator activity if not managed. Input weight. This penalizes rapid changes in the control input. A low input weight allows aggressive changes for faster response but may stress actuators or cause oscillations. A high input weight smooths the control signal, reducing actuator wear but slowing system response. Output weight emphasizes tracking precision. A high output weight ensures tighter tracking of the reference but can lead to excessive control effort. A lower weight allows more deviation from the reference but results in a gentler control action. In summary, higher prediction and control horizons improve foresight and flexibility but increase computation and potential instability. Higher input weights prioritize actuator health and smoothness, while higher output weights enforce tighter reference tracking. The tuning process involves finding the right balance for the specific system and performance objectives. Once the tuning of the controller is completed in the state space model, the controller is then used in the real system, and it can be seen that MPC controller is controlling the level of water very nicely. A PID controller can also be designed to regulate the water levels in tank 1 and tank 2. Since this is a multi-input, multi-output system, it needs to be converted into a single input, single output form for easier control. To achieve this, a decoupling control scheme is applied. This involves calculating and integrating a decoupler into the system as illustrated in the figure. When done correctly, the interactions between the tanks are minimized, allowing each control loop to behave like an independent SISO system. This enables us to tune each PID controller using standard methods. In this video, I'm using the auto-tune feature in Simulink to tune the controllers efficiently. Once tuned correctly in the decoupled scheme, PID controller is tested in the real system and optimized if necessary. Here, PID controller is working properly, so we are going to export the outputs and inputs in MATLAB workspace and plot the figures. This will give us the freedom of formatting the plots as we desire. Both of the controllers are able to control the level of the tank successfully, but if we have to compare, MPC controller is more accurate to track the set points with less overshoot and low settling time than PID controller. Don't forget to like, share, and subscribe for more content like this. If you have any questions or feedback, feel free to reach out. All my socials are linked in the description below. Thanks for watching, and I'll see you in the next one.